Hi, I'm Guang, 50 years old. In this lesson of applications and techniques of definite integration, we are taking a look at two different examples over here. So, the first example, let's take a look at it. Now, in this first example, you do see it's kind of a double integration, iterated integration form, where you have integrate from negative infinity to positive infinity. And you have square root x squared plus y squared cubed e to the power negative x squared minus y squared dx dy. So you might be wondering, can we draw the graph for this? Well, actually, you probably wouldn't want to draw it, since this is basically your entire x or y plane, which I have no idea how you're going to draw it, unless you want to draw like a 3D coordinate system where you have x, y, and the z-axis, and you just shade the entire x or y plane. Well, I don't know, it just depends on what you like. Right, so when we take a look at this that we have over here, how about we think of something else, something more simpler to solve this. We do see x squared y plus y squared. In fact, it always appears in x squared plus y squared. So do you think of anything else in order to solve this question? Well, of course, we would like to change this into polar coordinates. Now, in polar coordinates, you have square root r square cubed and e to the power negative r square. Then r dr d theta, and r is from 0 to infinity, while theta is from 0 to 2 pi. Well, you can also use r as negative infinity to infinity, or theta as 0 to pi. Okay, that just depends on what you like. Now, when we take a look at this, you will realize pretty much all the terms include r, except integrate from 0 to 2 pi d theta. So we can solve that part first. Well, we would immediately get 2 pi and then integrate from 0 to infinity. Alright? So then we can take a look at what we get inside here, which is r to the power of 4 e to the power of negative r squared dr. Right, now you might be, again, a little confused. How do we solve this? So, the simpler way to solve this, integral by parts. Integration by parts, you can put a half inside along with an r to make d r squared, and then of course you want to put your entire term with e inside, so you have negative pi integrate from 0 to infinity r cubed d e to the power negative r squared. And next you will be using your integral by parts in order to get negative pi r cubed e to the power negative r cubed, and then substitute r is equal to 0 to r is equal to infinity. And then you add on pi integrate from 0 to infinity e to the power negative r squared dr cubed. Now, the first term, if you know how to solve it, it's basically 0. Well, of course, you might be wondering, if you solve infinity, it's infinity times 0 form, isn't it? But then you can change this into a denominator and make it infinity over infinity, then use your L'Hopital's rule in order to solve it. So that should be simple. Or the bottom part, it's pretty obvious. 0 times 1 is 0. So when we take a look at this, we can move your r cubed outside to get 3 pi integrate from 0 to infinity r squared e to the power negative r squared dr. So we still can't solve it. How about let's repeat the entire process again, where you will see negative 3 pi over 2 integrate from 0 to infinity r d e to the power negative r squared. So this should be the term that you see, since when you put one r in, you have a half, they have a negative, and so that is what you will see. Next, of course, integrate by parts again. Integral by parts, so you have negative 3 pi over 2 r e to the power negative r squared. And whoops, this is not an r cubed, this is a negative r squared, sorry about that. And then integrate from 0, substitute in 0 and infinity, then plus 3 pi over 2, and then you will have integrate e to the power of negative r squared dr, and this boundary is from 0 to infinity. Right, so does this look more like a more solvable form? Well, of course, it is your Gaussian integral. So Gaussian integral, what is your answer essentially? It will essentially be square root pi. So you'll be having 3 square root pi cube over 4. Right, so that would be your final answer for your first example. Right, so again, what kind of processes did we use here? Firstly, change from Cartesian coordinates into polar coordinates. And when you change that into polar coordinates, you use integral by parts twice, and then insert your Gaussian integral to get your final answer of 3 square root pi cube over 4. Right? So I hope that you are clear of the first example so far, and I'll be moving on to the second example. So just get a last quick look of how question 1 is solved. Alright, so I'll be moving on to the second question now. Right, for the second question. So you have a double integration along x squared plus y squared small or equals to 1, which is a circle of radius 1 centered at the origin. And inside here, you have cubic root 4x squared plus 4y squared plus 1 dx dy. So again, you might want to use a similar method, since now it is more obvious with your boundary, since it is a circle of radius 1 centered at the origin. Right, so converting this into polar coordinates, well, of course, you can also choose to draw out the kind of graph you will be seeing. Right, so at the origin and radius of 1. And of course, it is your entire circle. Right, so changing it into polar coordinates, cubic root 4r squared plus 1 r d theta. And your boundaries will be r is from 0 to 1, or theta is from 0 to 2 pi. Alright? So this is essentially the kind of integration that you will have to solve. Right, so then you can take a look at it again. Are there any other terms with theta, or are they all just multiplied onto whatever integration you have with theta? Well, of course, the only part with theta that is multiplied on is integrate from 0 to 2 pi d theta, which is essentially just theta substituted in 0 and 2 pi, which gives you immediately a 2 pi. Then integrate from 0 to 1 cubic root 4r squared plus 1r dr. Now, how do we solve this part? How about firstly, we put the r inside to get your r squared, and then you put a 4 inside. So of course you have to divide by a 4 on the outside, and then you get a pretty familiar form, isn't it? Since you have, like, let's say y plus 1 to the power of 1 over 3, which then you can use your normal integration formulas in order to solve it. So pi over 4, integrate from 0 to 1, cubic root 4r squared plus 1, and then d 4r squared, right? So this is what you will be seeing. And next, what are we going to have? Now, since this is to the power of 1 over 3, that means when you integrate, it will become to the power of 4 over 3. And to the power of 4 over 3, that means you have 3 pi over 16, 4r squared plus 1 to the power of 4 over 3. Then substituting the values 0 and 1. So, putting in a value of 1, you're going to have 5. So 3 pi over 16, and you're going to have cubic roots 5 to the power of 4 minus, so when we put in 0, that will just be a 1. So this is the kind of answer that you will get, alright? So 3 pi over 16 cubic root 5 to the power of 4 minus 1. Right, so let's take a look at what we use for this example. Now, firstly, taking a look at its boundaries, it is much more simpler to use polar coordinates to solve it. So using polar coordinates, we make a simple exchange between the kind of coordinate system you're using, and then using simple integration methods, you arrive at your final answer. So between these two questions, you realize you are using polar coordinates for both of them, but there are a little bit of difference between these two examples, which is mainly in the boundaries. In the boundaries, the first question, you have basically the entire axis and the plane, right? But for that, since you see x squared plus y squared throughout the entire thing, it is much simpler to use your polar coordinates in order to solve it. Or for a second example, using polar coordinates is more obvious as you do have the circle boundary, right? So I hope for these two examples, you've covered everything so far. I'll be ending this lesson here, and thank you for your watching.